Hello everyone, I'm Jyoti from BSc Chemistry Honors second year. This video is specially for visually impaired students from inorganic chemistry, and the chapter name is Chemistry of Elements of second and third transition series. Let's start. In the previous chapter, we have discussed the position of transition elements in the periodic table. Transition elements belong to D block of the periodic table and are located in between the S block and P block elements in the periodic table. The D block elements involve primarily the filling of subshells. These subshells, the penultimate shell in these elements is being expanded from 8 to 18 electrons by the addition of 10 electrons. We also attempt to define the transition elements as elements which have partially filled d subshells either in the elementary form or in their commonly occurring oxidation states. Strictly speaking, this definition excludes zinc, cadmium, and mercury from the D block elements. This is because these elements do not have partially filled d subshells either in the elemental form or in their common oxidation state. The elements of group 12 do not show distinctly the properties of transition elements except for the ability to form coordination complexes with ligands. However, for sake of continuity and rational classification, the elements of group 12 are included in D block elements. In this chapter, we intended to explore the chemistry of heavier metals of D block, that is second and third transition series. The heavier metals of the D block are highlighted as given below. It is interesting to note that the 3D transition series, the atomic number of the elements of the second transition series, and sequentially is from deuterium to cadmium, sequentially from 39 to 48. However, there is discontinuity in atomic number between lanthanum to hafnium in the third transition series. In brief, the second and third transition series that involve the filling of 40 and 50 orbitals respectively include the elements with atomic numbers such as for second transition series these are deuterium to cadmium, that is 39 to 48, where 40 orbitals are gradually filled, while in third transition series lanthanum to hafnium, that is from 57 to 72, to mercury, that is 80, 50 orbitals are gradually filled. Electronic configuration of elements of second and third transition series. The general electronic configuration of elements of second and third transition series can be written as n-1 d1 to 10 ns1 to 2, where n-1 stands for the penultimate shell, which occupies 1 to 10 electrons in the d subshell, while n stands for the outermost shell that occupies 1 to 2 electrons in the s orbital. General characteristic of second and third transition series. We have noticed clear periodic trends down each group in the chemistry of S and P block elements. However, transition elements of second and third transition series show very strong similarities in their chemistry within a group but show large differences from the elements of first transition series. This similarity is due to the filling of 4f orbitals in the elements that lie between these two rows of elements. Electrons in these orbitals shield very poorly the electrons in outer 6s and 5d orbitals. As a result of poor shielding, the effective nuclear charge decreases, with the result that the aromatic, covalent, and ionic radii the period transition elements are reduced to almost the same as those in the period irregular or anomalous electronic configuration. In the first transition series, the 4s electrons are filled before the 3d electrons in the neutral gaseous atoms. From scandium onward, the 3d level continues to fill regularly with increasing Z, uh, uh, but at chromium there appears to be an anomaly. In case of chromium, the electrons are filled that the 4s and 3d orbitals are each half filled. This is due to the extra stability associated with the half filled orbitals. Similarly, at copper, the electronic configuration is anomalous behavior of extra stability associated with the completely filled d orbitals. However, elements of the second and third transition series displays much more irregular electronic configurations in addition to half or completely filled d orbitals. These are shown in bold letters as given below. Atomic and ionic radii. The atomic and ionic radii of elements of first transition series are well known. However, the atomic and ionic radii of second and third transition elements are not known with the certainty, with the exception of few elements. As we move down a particular family of the transition metals, the periodic group, there is an transition series which is negligible shown below. Oxidation states. The oxidation number of the transition metals are higher for the first half of each row than for the later members. Lower oxidation states are found to be more stable in case of first transition series compared to the elements of second and third transition series. The elements of second and third transition series have high common oxidation state from first transition series oxidation number than the first transition series. Like main group elements, the highest oxidation number of transition metal is found in case of oxides. Thus, the highest oxidation of osmium is 8 occurs in case of osmium, so for the other compounds that um, the other compounds that exist in high oxidation states which have no counterparts in the first row are, that is WCl6, ReF7 and PtF6. It is also interesting to note that the superficial similarities in the chemistry of second and third transition series elements exist to know that compared with the elements of first transition series. For example, chromium, molybdenum and tungsten all forms oxides with oxidation number +6. However, chromium oxide is highly oxidizing, whereas MO3 and the WO3 are normal oxides of these metals. Reactivity: the elements of first transition are more reactive than the corresponding elements of the second and third transition series. The lanthanide contraction is majorly responsible for the low reactivity of second and third transition series. As an example, gold and platinum are least reactive. At the low reactivity is due to the closeness of the valence electrons of the nucleus because of the poor shielding screening of 4f electrons. Because of poor screening of 4f electrons, the valence electrons are very tightly bound to the nucleus and are not readily available for the chemical reactions. Stability of the complexes. Transition metals have the ability to form complexes in contrast to S and P block elements. This is due to the small size, highly charged ion and availability of vacant d orbitals of low energy. In case of transition metals, the elements of first transition series form stable complexes with hard donors with N and F, whereas the elements of second and third transition series form stable complexes with PS and heavy halogen donors. Coordination number: the coordination number is 6 is commonly found in transition elements, giving an octahedral structure. The coordination number 4 is less common and gives either square, planar, or tetrahedral structures. Complexes with coordination number higher than 6 are less common for the first transition series but are common among early members of the second and the third transition series. Ligand transition series but are common among early members of the second and third transition series. Ligand repulsive interactions become more important with higher coordination number, and thus it is the smaller ligands which allows highest coordination numbers. There are only few compounds in which the coordination number is 7. There are three geometric forms known in this case and are shown as monocapped and octahedron, pentagonal bipyramid, and tetragonally capped trigonal prism as shown below. The capped octahedron is shown by tungsten complex with is shown here. Capped octahedron is formed by the addition of seventh atom to the center of any face of the uh, octahedron. The pentagonal bipyramid geometry is adopted by the anionic species. Tetragonal capped trigonal prism is adopted by MF72 negative, where M is equals to NBOT. This arrangement is shown by putting a seventh atom above the center of one of the rectangular faces of trigonal prism. Um, Coordination number greater than 7 are also known among the second and third row transition elements. Coordination number 8 is found in the square antiprism as in Na3. Coordination number 9 is the limit for covalently bound D block metal complexes because this full use of 9 valence orbitals. Anion REH92 negative has trigonal primestic structure with coordination number 9. Aqueous chemistry. Elements of first transition series have very rich aqueous chemistry. As an example, cobalt forms a variety of tetrahedral and octahedral complexes and display interesting aqueous chemistry. On the other hand, corresponding members of the second and third transition series with second and third do not such complexes and consequently do not have the aqueous chemistry. However, most of the heavier transition metals, instead of forming simple cationic complexes, prefer to form aromatic complexes in the form of halo compounds and holo compounds. And ionic complexes of heavy transition elements have rich aqueous chemistry. Magnetic properties: compounds with non-paired electrons are diamagnetic, while those with one and more unpaired electrons are paramagnetic. Most of the transition element compounds are paramagnetic. The diamagnetic arises from the circulation of electron pairs and induced by the presence of the applied magnetic field. This characteristic circulation produces an induced magnetic moment, which opposes the applied field and leads to the atom or molecule being repelled by it. On the other hand, if unpaired electrons are present, the applied field induces a magnetic moment which is aligned with the magnetic field. This effective causes the sample to be attracted into the magnetic field. Paramagnetism results from the interaction of the spin and the orbital angular momentum of the electrons with the applied magnetic field. If there is no interaction between the spin and the orbital angular momentum, the magnetic moment mu s plus L1 atom or ion is released to the total spin quantum number s and the total angular momentum quantum number L by the expression. Metal bonding. Metal bonding is very rare in the first transition series except in metal carbonyls such as Mn2Cu10, and in carboxylate complexes such as chromium acetate and in solid nickel dimethyl diglyoxide. So, on the other hand, metal bonding is very common. Almost the heavy transition elements of second and third transition series, for example, they form carbonyls with bonds similar to those of the first transition series. The heavier metals such as MORUH form binuclear carboxylates complexes such as MO2CS3. Uh, the halide ions of the type C2 Cl8 2 negative and MO2 Cl9 3 negative possess bond. A unique feature of set of five elements of the second and third transition series is that these form clusters in which there is extensive metal bonding. The complex NB6C12 2 positive and TH6Cl12 2 positive have unusual structures. Both the cationic spaces contain six metal atoms arranged in cluster of at the corners of an octahedron with 12 brazing halogen atoms across the corners. In these clusters, there is an exam survive bonding as shown in figure. Unlike the lower halides of 3D series, the lower halides of MO and W exist as hexamers, that is MOXC12 and W6C12. These present interesting structures as where M equals to M and W, X equals to Cl. Six metal atoms are arranged, that is clustered at the corners of an octahedron with eight halogen atoms located above each of the eight faces of the octahedron and bonded to the three metal atoms as shown. Chemistry of ReCl3 is interesting as it exists a trimer, that is KReCl3. It consists of a triangle with three relations with three brazing halogen atoms across the three corner and six halogen atoms that bridge to other Re3Cl9 units as shown below. Abundance. All the first transition elements are widely distributed throughout the Earth's crust and the So the next property is abundance. All the 10 first two transition elements are widely distributed throughout the Earth's crust and the oceans. Iron is the fourth after oxygen, silicon, and aluminium. Titanium is the ninth, while manganese is the 12th most abundant element by weight in Earth's crust. The remaining transition elements of second and third transition series are very scarce and Taken together, these 20 transition elements constitute only 0.025% of Earth's crust in comparison with 6.2% of all the 10 first row transition elements. Molybdenum is a unique element amongst all the second and third transition series that plays important role in human body. Technetium does not occur in nature. Ionization energies. The first ionization energy of an atom is the minimum energy required to convert the mole of the gaseous atom in its ground electronic state into the mole of the gaseous unipositive ion. The amount of energy required in this process indicates how strongly the most loosely bound electron is attracted by the nuclear charge. It has been observed that the in case of with which an electron can be removed from a transition metal atom is intermediate between those of S and P block element. The first ionization energy and the successive second and third ionization energies of the transition elements are plotted. An inspection of the figure as given below carefully reveals that the third transition energy increased more rapidly than the first and second ionization energies. As a result, these transition metals are better indicated by their third ionization energies. The variation of third ionization energies of these sets of transition elements from scandium to zinc, yttrium to cadmium, and lanthanum to mercury shows there is a general increase in ionization energy with the discontinuity after group 7. This discontinuity in the values correspond to the ionization from a doubly occupied d orbitals. Is that electronic configuration of F is 26, that is 3d6 4s2. The third ionization energies from atom of group 8 to 12 are from doubly occupied d orbitals and consequently lower because of the increasing repulsion between the paired electrons in the same orbitals in the subsequent elements. The discontinuity between manganese and iron in the first transition series and between technetium and ruthenium in the second transition series reflects additional energy required to break into half-filled subshells of Mn2 positive and Tc2 positive, which involves the maximum loss of exchange energy. Similarly, in case of europium, the third ionization potential does increase in the third transition series where the 4f7 configuration is reached. Thereafter, it falls back and then increases again on approaching the configuration at YB82 positive. In brief, the ionization energies increase irregularly across three transition series and is for less regular in third transition series. In addition, towards the end of the transition series, the d orbitals become more core-like. As a result, these are less effective in stabilizing higher oxidation states through covalent contribution of bonding. Taken together, these factors might make higher oxidation state less accessible to the right of the d block. In addition, there is greater loss of exchange energy in creating PD4 positive from PD2 positive than ZR4 positive from ZR2 positive. Now we will talk about the comparative study of the elements of second and third transition series. We have already discussed the general characteristics of the elements of second and third transition series with special reference to the elements of first transition series. In the preceding section, we will talk to highlight the chemistry of elements in different groups of second and third transition series. An attempt will also be made to compare the chemistry of these elements with the elements of first transition series. Group 4, zirconium and hafnium. Group 4 consists of the elements titanium, zirconium and hafnium. Some of the unique properties of these elements are summarized below. As electronic configuration of titanium is 3d2 4s2 and zirconium is 4d2 5s2, while that of um, hafnium is 4f14 5d2 6s2. We have already remarked that the atomic and ionic radii of the transition elements in a particular series decreases with increase in atomic number. However, compared to S and P block elements, the decrease in the radii along a particular series is not regular and uniform. In case of group 4 elements, both zirconium and hafnium have larger atomic ionic radii than titanium. However, an inspection of the table reveals that both the Atomic and ionic radii of zirconium and hafnium are identical. As a result, these elements have similar chemistry. This is primarily attributed to the effect known as lanthanide contraction. All the elements possess outside a noble gas core, that is D2S2 configuration. The significant difference of zirconium and hafnium from titanium is, unlike titanium, zirconium and hafnium only forms a few compounds in oxidation state below 4. Most of the stable compounds are in oxidation state 4. Both zirconium and hafnium form the binary tetrahalides. The tetrahalides can be prepared by the standard methods. All the tetrahalides in the gaseous state are monomeric and tetrahedral, but in the solid state these are octahedral. Coordination through halogen bonding. The tetrahalides are readily hydrolyzed. The extent of hydrolysis, however, decreases from titanium to zirconium. TiX4 compounds are hydrolyzed to TiO2, whereas ZrX4 and HFX4 hydrolysis to give ZrOx2 and HFOx2. ZrCl4 is hydrolyzed vigorously by water at room temperature to give oxychloride, which is stable to further hydrolysis. The complex ZrOCl2 which crystallizes from dilute HCl, has been shown by X-ray to contain the ion, as shown below. Each zirconium atom is surrounded by 8 oxygen atoms, um, 4 oxygen from 4 coordinate water and 4 oxygen from freezing OH groups. The coordination number of each zirconium atom in this complex is 8. Like titanium chloride, ZrCl4 and HFCl4 are known to act as good Lewis acids. Therefore, these react with neutral ligands to form the stable adducts of the composition MX4, 2L, where L equals to triphenyl phosphine ether, etc. Zirconium and hafnium have a high charge in +4 oxidation state, and there is no partially filled D subshell that might give stereochemical preferences and have relatively large size. As a result, the tendency to assume higher coordination number increases with ZR and HF. Examples where the coordination number reaches 7 or 8 are known with oxygen and fluorine ligands. The structures of the anions are shown below. The species ZrF3-7 is basically a trigonal prism with an extra ligand attached to one face. Oxidation state thought. The reduction of the tetrahalides with respective metals at high temperature and pressure yields the trihalides, which are colored compounds. The well-known compounds of in third oxidation state are ZrCl3, ZrBr3, ZrI3, HFCl3, and HRBr3. HFBr3. Group 5, niobium and tantalum. So, group 5 consists of the elements vanadium, niobium, and tantalum. Some of the unique properties of these elements are summarized below. First of all, we will see their configuration, electronic configuration. The electronic configuration of vanadium is 3d3 4s2. That of niobium is 4d3 5s2. That of tantalum is 4f14 5d3 6s2. Niobium and tantalum occur generally together and are separated by fractional crystallization of their fluorocomplexes. The atomic and ionic radii of niobium and tantalum are almost similar but greater than that of 3D analog, that is vanadium. Although both niobium and tantalum are metallic, their chemistries in fifth oxidation state are more similar to those of typical nonmetals. As a result, they do not form cationic complexes um, characteristic of a metal. Instead, these form variety of anionic complexes typical of a non-metal. The coordination number of niobium and tantalum is these anionic complexes are generally 7 and 8. The stable binary of oxides of niobium and tantalum are the pentoxides, which are the dense white powders. These are obtained by the ignition of other niobium and tantalum compounds in air. These are very stable oxides and extremely difficult to reduce. Halides and oxohalides. Niobium and tantalum form all the halides in their high oxidation states. The pentafluorides are obtained by the reaction. A unique feature of niobium is that it forms the stable pentaiodide. The pentafluorides are volatile white solids melting below 100 degrees Celsius and boiling nearing 230 degrees Celsius. They have a terameric structure that is characteristic for other pentafluorides units and bridging fluoride between each pair of metal atoms, as shown below. The pentachlorides are yellow crystalline solids that are obtained by direct reaction of the metal with chlorine. X-ray study revealed that NbCl5 is dimer in the solid state with two bridging chlorides, giving an octahedral configuration around each niobium. The halides are readily hydrolyzed to give oxyhalides of the formula MOX3. The oxyhalides are covalent but less volatile than the corresponding pentahalides. The structure of NbOCl3 is polymeric and shown in figure. The oxychloride contains planar trinuclear tops which are linked into long chains by oxygen bridges between the niobium atoms. Niobium pentachloride Nb2Cl10 is reduced by pyridine to give niobium complexes of the type NbCl4. Both the pentachloride are strong Lewis acids and give adducts with neutral donors. They also form complexes in ions with halide ions. For example, both the pentachlorides form fluorocomplexes. Lower halides. The lower halides of niobium and tantalum deserve special mention. These lower halides are prepared by the reduction of the pentahalides either by heating with the metal itself or with aluminium. Earlier, it was considered that the lower halides of niobium and tantalum were non-stoichiometric. However, it has been shown that most of the lower halides are in fact cluster compounds containing the basic unit M6X12 positive. The octahedral M6 units are held together by MM bonds which over the 6 metals atoms in addition to halogen bridging along the 12 edges of the octahedron. An interesting example of the lower halide of niobium is Nb6Cl14. It is made by reducing niobium pentachloride with cadmium metal at a red heat, dissolving the product in dilute HCl and recrystallizing from the solution. The chloride Nb6Cl14 consists of discrete ion as shown in figure. Group 6 molybdenum and tungsten. Group 6 consists of elements chromium, molybdenum, and tungsten. Some of the salient features of these elements are summarized below. As electronic configuration of chromium is 3d6454s1, molybdenum is 4d55s1, and tungsten is W is 4f14, 5d4, and 6s2. Molybdenum and tungsten have the atomic and ionic radii nearly similar but possess greater value for the corresponding first element, that is chromium in the group 6. On account of similar radii value, molybdenum and tungsten possess nearly similar chemical properties. Group 6 elements displays valences ranging from group valence plus 6 down to 0. The valence plus 6 is the highest for all the elements. Molybdenum and tungsten in the plus 6 R state are the most stable and the most common state. It is important to note that in case of chromium, the plus 3 state is the most common and stable state. It follows that the higher valent chromium, especially in the plus 6 state, will be strong oxidant. In fact, chromium in the plus 6 state is the strongest oxidizing agent. On the other hand, MO third and W third are strongly reducing. The trioxides of MO and W are obtained by heating the metal or the other compounds in air is a white, whereas WO3 is a yellow solid. Unlike CrO3, the trioxides of MO and W are insoluble in water. MO3WO3 are not attacked by acids other than HF in alkaline medium. These dissolve to form molybdenate and tungstates that are tetrahedral in shape. Anions such as MO2 negative or WO2 negative or containing only one kind of metal atoms are called isopolyene ions, whereas anions containing more than one metal atom are called heteropolyene ions. An interesting example of heteropolyene ion is found during the molybdenate test for phosphate when yellow precipitates are formed from the composition. The heteropolyene ion is PMO12O43 negative halides. Interaction of molybdenum and tungsten with the element fluorine gives colored covalent hexafluorides. Fluorination of molybdenum gives only the dark reddish dimeric pentachloride solid. MO2Cl10 has the structure similar to the Nb2Cl10 as discussed below. The molybdenum and tungsten dichloride, dibromide, and diiodides are isomeric and in the solid state contain halide bridged clusters. These clusters are in isostructure with ions as discussed earlier. The structure also contains metal-metal bonding in MO6 cluster. In the lower oxidation state, there is a greater tendency for metal-metal bonding as in case of MOW forming MO2Cl3 negative and W2Cl9 3 negative ionic species wherein 2 MlCl6 octahedra share a phase as shown below. In the corresponding Cr2Cl9 3 negative, the Cr-Cl distance pair commeter, it shows that the normal magnetic moment corresponding to 3 unpaired electrons. It further implies that there is no Cr-Cr bond in Cr2Cl9 3 negative. On the other hand, low magnetic moment values in MO2Cl9 3 negative and practically diamagnetic character in case of W2Cl9 3 negative suggest appreciable metal bonding in case of molybdenum tungsten ions. This is further supported by the bond distance in case of molybdenum and tungsten compared to 312 picometer in case of chromium. Interaction of molybdenum hexacarbonyl with carboxylic acid give a dimer with a unique tetrahedral bonding treatment of MO2 with KCl and HCl yields the compound containing unique anion. The bonding between two molybdenum atoms shown below is called quadrupole bonding. It involves the sigma and 2 pi 1 sigma 2 pi 1 delta bonds between two molybdenum atoms. It is interesting to note that two MOH4 units shown in the figure are equivalent configuration to each other. Technetium and rhenium. Group 7 consists of elements manganese, technetium, and rhenium in the periodic table. The salient features of these elements are summarized below. Their configuration are: for manganese it is 3d54s2, for technetium it is 4d55s2, for rhenium it is 4f14 5d56s2. Technetium and rhenium have atomic radii more than manganese. Group 7 of the periodic table. Although technetium and rhenium form some compounds that are analogous of those manganese, there is very little chemical similarity. Otherwise, some of the features that makes the chemistry of technetium and rhenium different from the manganese listed below. Unlike manganese, which is most stable in plus 2 oxidation state, there are very few stable complexes known in case of technetium and rhenium in plus 2 oxidation state. There is very little cationic chemistry in case of technetium and rhenium, not only in any oxidation state, even in complex compound. But technetium and rhenium have a very rich chemistry in the oxidation state 4 and 5th, especially as oxo compounds in 5th oxidation state. Unlike paramagnetic MnO4 negative ion, which is the strongly oxidizing ion, the corresponding oxotechnetium and rhenium ions in oxidation state, that is 7, are not oxidizing at all. Unlike manganese, both technetium and rhenium display extensive metal-metal bonding in 2nd and 3rd oxidation state. All the non-isotopes of technetium and radioactive 99 technetium can be easily prepared these days as one of the fission products of uranium. This has a half-life of 2,12,000 years and is a weak beta emitter. It is thus mildly radioactive and can be easily handled. The non-binary halides of technetium are TCF6, TCF5, TCCl4. On the other hand, rhenium forms a large number of binary halides. For example, rhenium combines with fluorine to form ReF6 and ReF7 with octahedral and pentagonal bipyramidal geometry respectively. ReF6 gets readily hydrolyzed to ReF4 and eventually to a mixture of ReCl2, HrEO4 and HF. It can be easily reduced to ReF3 and ReF4. Chlorination of rhenium yields a variety of compounds with ReCl6 and Re2Cl10. The latter compound is more important and can be prepared by the reaction of chlorine with metal at 400 degrees Celsius or by the action of CCl4 on Re2O7 and 400 degrees Celsius. The thermal decomposition of ReCl5 leads to the formation of rhenium chloride, which exists as a trimer Re3Cl9 with the structure. The terminal chloroligands lie above and below the plane containing the Re and bridging Cl atoms. The Fe Re bond lengths are 248 picometer and each bond is hence a bond order of 2. Interestingly, there is no technetium analog of Re3Cl12 in the solid state. 2/3 of the terminal chlorine atoms in Re3Cl9 are involved in a weak bridging interaction to rhenium atoms of adjacent molecules, Re units. Please note that both Re and Re' belong to two different molecules of Re3Cl12 and each Re atom is thus associated with 5 Cl atoms. The ability of rhenium atoms in Re3Cl9 to interact with electron donors plays an important role in its chemistry and the addition of ligands to the in plain sites shown below. The compounds can be isolated from Re3Cl9 in aqueous solution at 273 K. Similarly, the compound Re3Cl9P3 can be isolated from the reaction of Re3Cl9 with pyridine. An interesting compound containing the complex ion can be obtained by reducing the perhenyl ion in hydrogen in HCl. The Savary complex is isostructure with described earlier. There is Re triple bond Rv in this anion as the Re distance is extremely short. As already pointed out that unlike magnesium, rhenium and technetium compounds in 7 oxidation state are more stable. An interesting example is provided by the hydrogen complex K2ReHN K2CH9 obtained by treatment of perhenyl or pertechnetion ion with potassium in mixture of ethylene diamine and water. The structure of the ethane hydrohenium ion is in brief, because of the larger atomic size of technetium rhenium in comparison to manganese, the various stereochemistry adopted by the heavier members are summarized below. Group 8, 9 and 10. It is important to point out that the horizontal similarities, that is iron, cobalt and nickel, much greater than anywhere else in the periodic table except among the lanthanides. However, the second and third rows transitional elements have similarly, because of lanthanide conduction, similar properties. The 6 heavier elements of the group 8 are rhodium, osmium, ruthenium, osmium, rhodium, iridium, palladium and platinum. Listen again: ruthenium, ruthenium, osmium, rhodium, or iridium, palladium and platinum are properly considered as platinum metals. They are elements, platinum being the most common with natural abundance as metals of abundance of 10 raised to power 6% compared with the other 5 heavy metals of order of 10 raised to power 10%. All the 6 elements occur either as metals of an alloy such as osmiridium, that is an alloy of osmium and iridium. These elements are usually associated not only with the another but also with nickel, copper, silver and gold. The chemistries of platinum metals, that is ruthenium, osmium, rhodium, iridium, palladium and platinum, have some unique common features. In addition, these are several variations in their properties depending upon the differing stabilities of oxidation, side states and the stereochemistry associated with the compounds formed. There is very little similarly of platinum metals with that of its union, and except in carbonyl compounds. Carbonyl compounds are compounds of metals with pi-acid ligand like carbon monoxide. In order to appreciate more the important oxidation states of platinum are listed below. Group 8, ruthenium and osmium. Iron, ruthenium and osmium constitute the elements of group 8 of the modern periodic table. Some of the salient features of these elements are described below. The effect of the lanthanide contraction is less significant in the elements of group 8 of the periodic table. As a result, the similarities between the elements of second and third transition series are not so close are found in case of early transition groups. The close horizontal similarities in the ferrous metals and in platinum metals are largely due to the similarities of their atoms and ions in size. Osmium, being little larger than ruthenium, is expected to have a much higher density because of its compactness. As a result, OS is the second most dense element. One of the most characteristic features of chemistry of Ru and OS is their oxidation. To give the volatile tetroxides, orange-colored RuO4 is formed when acid solutions containing ruthenium are oxidized by a MnO4 negative ion or Cl2 gas. OSO4 is formed by treating the metal either by burning in oxygen by reacting with concentrated HNO3 of 2 tetroxides. RuO4 is more stable. They have tetrahedral structures. In brief, because of the larger size of osmium and ruthenium in comparison to iron, the various stereochemistries adopted by the heavier elements with geometries are summarized below for ready glance. Rhodium and iridium. Cobalt, rhodium and iridium constitute the elements of group 9 in the modern periodic table. Some of the salient features of these elements are summarized below. Unlike cobalt, the heavier elements rhodium and iridium occur only in F6 and IRF6, which are obtained by the direct reaction of the metal with fluorine. IRF6 is more stable than RHF6. Cobalt plus 5 compounds similarly do not exist under normal conditions, whereas RH plus 5 and iridium plus 5 exist as pentafluorides, which are tetrameric with the formula RHF420 and IR4F20. The small ionic sites of the heavy elements lead to variety of complexes. The known complexes of rhodium iridium plus 5 oxidation states are CAS, RHF6 and CSIRF6. Both rhodium and iridium form tetrafluorides. Rhodium fluoride can be prepared by RHCl3 and BRF3 plus 4 is one of the most stable states, but RH plus 4 is unstable and form only few compounds. Other compounds in plus 4 oxidation state are characterized by RHO2, IrCl4 and complex anions. The chloride complex is conventionally prepared by the reaction of RH with NaCl in the presence of chlorine. The best known compound of rhodium is the red colored complex. On boiling with water it gives, and with NaOH it gives RH2O3H2O. Rhodium and iridium give an interesting class of square planar complexes which are used in homogeneous catalysis. The stereochemistry of well-known rhodium compound, that is RHCl3P PH33, and is known as Wilkinson catalyst. It is prepared by the reaction of RHCl3 with triphenyl phosphate. In conclusion, the various oxidation states accepted by the heavy elements together with their geometries are compiled up in the table as given below. Group 10, palladium and platinum. Nickel, palladium and platinum constitute group 10. The modern periodic table, some of the salient features of the elements are summarized below. Nickel, 22nd most abundant element by weight in Earth's crust. Palladium and platinum are the rare elements but are appreciably more abundant than the platinum group metals. Palladium and platinum do not form the simple carbonyl compounds like nickel, which forms nickel tetracarbonyl. The important oxidation states of palladium and platinum are the second and fourth. Palladium and platinum exist as oxides, halides, nitrates, sulfates. Aldehyde halides are known except for PTF2. It is important to note that unlike the other halides, PTF2 is ionic. The beta form of PtCl2 and PtCl2 have unusual molecular structure based upon the Pg6C12 unit. The structure is nicely described as the metal being surrounded by 4 chlorine atoms in a square planar environment with 6 such units linked by halogen bridges. It is interesting to note that the structure resembles that of cluster compound in which 6 niobium atoms were linked in an octahedral cluster with the halogen atoms as bridging all the 12 edges. It is a cisplatin that is used as anti-cancer drug for malignant tumors. It is injected in the bloodstream and is the more reactive Cl groups that are lost. As a result, platinum atom bonds to the N atom of the DNA molecule and inhibits cell division. The other only definite example of +6 state for platinum are PTO3 and PTF6. So group 11 elements, copper, silver and gold, also referred as coinage or currency metals, are placed in group 11 of the periodic table. Some of the salient features of this group are as listed below. These are noble metals and often alternative in nature. All the elements of group 11 are known for their highest electrical and thermal conductivity in the periodic table. Although these elements in their atomic states have filled D subshell, these are considered as transition elements because their +2 and +3 states possess completely filled D subshells. Typically, these elements exhibit variable valencies. Although copper, silver, and gold display similar electronic structure and possess high ionization potential, yet there are limited similarities between their properties. The most common oxidation state of silver is +1, that is it forms a variety of salts with various anions in +1 oxidation state. With the exception of nitrate, pentachlorate, and fluoride, most of the other salts of the silver +1 are insoluble in water. The commonly heard silver chloride is insoluble in water. Structures of silver salts are usually similar to those of alkali metal salts. The most usual coordination number of silver is 2 with sp hybridization. The linear coordination is achieved with L is real angle is 180 degree with L is monodentate ligand. The linear structure cannot be achieved by bidentate chelating ligand. For example, AgCl reacts with ethyl diamine and give a dimeric species with an EN acting as a bridging ligand instead of chelating one. The sp3 hybridization sulfur atom in AgSCN is this responsible for the zigzag structure. The other less important oxidation state of silver is plus 2 plus 3. Fluoride is very important fluoridating agent. It is obtained by fluorination of AgF by green reaction of AgF3 next. In the earlier transition groups, we have noticed the general trend where higher oxidation states are more stable with the heavy elements. However, group 11 we found the gold plus 3 state the most stable and common state, whereas in case of silver we have already mentioned that plus 1 is the most stable and common oxidation state, whereas plus 2 is the most and common oxidation state as case of copper. Gold forms a variety of compounds with halogen, the most important being AuF3, AuCl3, AuBr3, AuI3 is not known. AuCl3 is conventionally prepared by dissolving gold in aqua regia followed by evaporation. AuCl3 and AuBr3 are also obtained from the elements and possess a planar diameric structure in both the gaseous as well as the solid state. The fluoride, that is AuF3, is made up of square planar AuF4 units linked into chain basis fluoride bridges. AuCl3 and AuBr3 react with the chloride and bromide ion to give the corresponding tetrachloride or tetrabrom aquid ion. The chemistry of gold is much richer than silver as it displays several oxidation states ranging from plus arranging from 1 to 3rd and 5th. It is important to note that 1 and plus 5 oxidation state known in case of gold have no counterpart in the chemistry of silver. AuF5 is the only plus 5 compound known. It is formed as a dark red dimagnetic polymeric solid by warming O2 positive, AuF6 negative, and considering the ivory product. AuF5 is not very stable and decomposes to AuF3 and F2 above 60 degrees Celsius. Cadmium, mercury, heavier elements. Zinc, cadmium, and mercury consist the elements of group 12 of the modern periodic table. The salient features of the elements of group 12 are listed below. These elements all have D10s2 configuration and typically form M2 positive ions. All the elements and their ions of group 12 have the complex D shell. These group of elements do not qualify themselves to be typical transition elements. However, because of the complexing ability of these elements with ligands, these are included in the transition elements. Zinc and cadmium display similar chemistry, whereas behavior of mercury is appreciably different from that of zinc and cadmium. Mercury is unique in many respects, that is that it is a liquid at room temperature and is a noble metal. Both zinc and cadmium react with non-oxidizing acids to liberate hydrogen. In addition, mercury is the only one element in the group that forms compounds in plus 1 oxidation state. The increased stability of the lowest oxidation state in the heavier elements in the group is more typical of the p block elements than the transition elements. All the elements of the group form the dihalides with fluorine, bromine, and iodine. Thus, all the 12 dihalides are well established. The fluorides have appreciable higher melting points than the other halides and appreciably ionic. The melting points of the fluorides, bromides, and iodides are fairly low and suggest these halides to be more covalent. Mercury forms an interesting class of Hg compounds in which two mercury atoms are bonded together. Mercury is unique, forming stable dinuclear metal ion Hg2 positive. All the mercury halides are known. Hg2F2 is hydrolyzed by water and then this proportionates Ng2Cl2 Hg2Br2 Hg2I2 are all insoluble in water. The nitrate Hg2NO3 2H2O is soluble and contains the linear S2HgHgOS2 ion. All these elements form oxides and sulfides MS by heating the elements together. On stronger heating, Hg composite has been used for the preparation of oxygen. All the three elements form insoluble sulfides. CDS is yellow, HGS is black, whereas ZNS is white. Thanks for watching.